In stats, we took things a little further and went from the empirical rule and predicting based on only 1, 2, and 3 standard deviations. And we looked at the standard normal curve so that we could make a prediction on percent for any number of standard deviations. In other words, like less than 1.2 standard deviations or something like that. So what I'm talking about here is the standard normal curve. And this is what Gauss discovered or derived, however you want to call it. But this is also known as the z-curve. It's typed right there, but this is also the z-curve. So the z-curve, it is normal, obviously. It has a center, a mean of 0, and a nice standard deviation, let's draw a better sigma, of 1. So this is called the standard normal curve, right here. If you have your formula chart handy, this whole curve is on the formula chart. So on the formula chart, if you go to table A, so here's the front page, flip a couple pages, and here's table A. This is the standard normal curve. It's 2 pages long. Notice top left right here it says table A, and then again right here it says table A. This is, and notice it says standard normal probabilities. This is the standard normal curve. Or you can just call it the z-curve, and notice here's z. So if you need to write the characteristics down, this thing is normal with a mean of 0 and a standard deviation of 1. All right? So when you look up a z-score, so we're getting away from real-world data for a minute. When you look up a z-score, what this table does is it calculates the area to the left of it. So it has an upper bound and no lower bound. So the lower bound is infinity for this table. So when we access the function in the calculator, it's going to be a little bit different. But for this table, for table A here, lower bound is negative infinity. It just goes on for forever. I mean, technically it doesn't go on for forever, but in theory it has no lower bound. It just goes on forever. There's not, notice the smallest z that's printed right here is negative 340, and there is 0.0003 data left of it. So when I say lower bound is negative infinity, I mean it doesn't go that far. There's nothing, I don't know, I don't think there's any data smaller than negative 5. It gets pretty microscopic out there. So, but lower bound is negative infinity, and upper bound is the z you're looking at. Z-score referenced, which is right here in the left column. So whatever z-score you look up, that's the upper bound, and it's measuring the area to the left. Now this z table, this table A, works kind of weird. So on the left column, you see all the way to the tenths, but at the very top, you see hundredths. So for example, this number right here, let's pick one that's unique, because I see a lot of 0.0003s. So let's go with 0.0041 there. So this number right here, that is the proportion to the left of a z of negative 2.64. Let me write that down. That is the proportion of z-scores smaller than negative 2.64. And that proportion is 0041. All right? Everyone see how to work it? If you go in the first column, like right here, 0359, that is negative 1.8, because top of the column there says 0, 0. So, for example, proportion of z's smaller than negative 1.8 is 0.359. All right, I hope that makes sense to you. This is 2 pages long. This is the left of the mean, small z's, negative z's, and then this is the right of the mean, but it's still measured the same exact way. So, for example, if I am looking at this 6736 number right here, that is the proportion of z's smaller than 0.45. So hold that thought right there. Like, remember that proportion, 6736. That's the proportion of z's smaller than 0.45. There's a way to do this on the calculator, and some like it better. So if I go to the calculator and get to a blank screen, press Menu, go to Stats, Distributions, and Normal CDF. I'll do this again. Menu, Stats, Distributions, Normal CDF. We will never ever click on PDF in this class. We will click on binomial PDF down the road, but not normal PDF. We're always going to do normal CDF. I want a lower bound of negative infinity if I'm trying to match what I just now wrote down right here, because that has a lower bound of negative infinity, like no bound on the left, but the upper bound is 0.45. So that means I keep that. That's negative 999. That's a tiny, tiny number. And 0.45, notice the mean is already 0 and the standard deviation is already 1. That's referencing the normal curve, the standard normal curve. And look at that, 6736, exactly what the table gave us. The nice thing about this normal CDF is you can be more precise than the table. I mean, you guys see it right there. It goes more digits out than just 4. So what if I wanted to be more precise and go 0.4591 of a z-score? I can be that precise. And notice the proportion does change. So there's that, but they're going to ask harder questions than that. So when we look at something like example 2 in your notes, you know, it starts out pretty nice, pretty easy. This is referencing the empirical rule. We know it's about 0.68 according to the empirical rule. But with the normal CDF thing, you can be more precise. Normal CDF says the answer is exactly I'll show you instead of just tell you. -1 up to +1. So we think it's going to be about 68. Let's see. 68.27 to be precise. If for some reason you wanted to use the table, it's a two-step process. You got to do the proportion of z's smaller than 1 and subtract the proportion of z's smaller than -1. So if you want to do that, you are welcome to do that. You have to look up two things and then you subtract them. So that is, let's go to the table. Here's +1, so 8413. See, I don't want to write on the screen because I'll lose my work that I just wrote, but if you look in the left column, look for 1.0, and just to the right of it, 8413. Now let's look up -1. There's a -1 on the left. Just to the right of it, 1587. And when we type that in, we get 6826, which is about what the calculator gave us. Sometimes the fourth place value is a little off, and that's all because in the table, they rounded to the fourth place, and in the calculator, it doesn't have to round at all. So, because of rounding, the fourth place is a little off, but I think you guys get the idea. So I already answered z's less than 1. According to the table, we know that answer is 8413. That's a case where maybe using the table is faster than the calculator, because that is just a less than question, and you can look that up and just write the answer down. If you want to use normal CDF, then you got to cleverly make the lower bound -infinity negative a bunch of 9s, and the upper is a 1. So when you do that, I pulled it up on my calculator, I typed in a 1 for the upper bound. Sure enough, we get 8413. Which is the same thing the table gave us. All right, let's get more precise, and that's what I'm talking about, where the empirical rule just doesn't quite cut it. So what if I want to be more precise, and for some odd reason, I'm interested in -1.25 standard deviations up to +1.25. So I jump to the calculator, and I type in that lower bound and upper bound. And I get 7887. And you can do that for the rest of these. So maybe try it out. See if you get the same answers as me. We got another lower bound of -infinity on that second question, and an upper of 0.81. And on that one, you should get 0.7910. So they flip it around and they give you a greater than on the next. This one, the lower, is -1.78. And this time the upper is +infinity, so a bunch of positive 9s. And on that one, you should get 9625. And lastly, if I go -125 up to 0.81, you should get 6854. All right, I hope that helps. This is just a crash course in the standard normal curve. We will practice it more down the road. See y'all later.